Hello, everyone. Today I'm going to be talking to you about one of the most important analytical tools for examining relationships between two or more variables, and that is regression analysis. And more specifically, today we'll be looking at simple linear regression analysis. So the idea over here is that I want to come up with some sort of an equation to describe or sometimes predict the linear relationship between two variables, x and y. And so a simple linear regression model will do that job. In a simple linear regression model, we need to identify the different components. So we've got here the dependent variable or response. That's usually your y, and that is what we wish to understand, explain, or predict. And then we've got our independent or predictor variable. That is usually our x, and that will serve to explain or predict the dependent variable. So let me go here and show you the form of the simple linear regression model. This is what it looks like right here. So you've got your y is equal to beta naught plus beta 1 times x plus your epsilon. Epsilon here being, well, I'm going to get to that in a little bit. It's your error term. So you can think of the simple linear regression model as being made up of two components over here. You've got your this component right here, which we call the mean level or the mean value of y. And so this mean level is represented by the symbol mu of y, and it is equal to exactly this portion of the simple linear regression model. It is equal to the beta naught plus beta 1 times x. Okay, so this looks a lot like a line equation. If you remember from before, we saw that a straight line equation was made up of a b, which is the y-intercept, and a slope uh, times x, right? So mx over here. So we see some similarities here between the mean level equation and a straight line equation, okay? Hence, we can call the mean level or the mean value of y as the line of means, okay? Then the other component that we're going to look at in a simple linear regression model is the error term, otherwise denoted by epsilon. The error term over here is simply the difference between your observed y and your mean level. And hence, the error term accounts for this random component that you get in a simple linear regression model that causes the y's over here for each x. So the y's for each x to deviate from the mean level. Okay, that is why here we see this type of form to express an error term. We see that it is in fact the result of a deviation or a difference between an observed and a mean or expected value, if you want. Okay, okay, so let's continue on over here. So if we have a straight line equation for the mean level, then basically we're going to have to solve for the y-intercept and the slope. And so that will be done, of course, when we start to look at sample data. So sample data means, of course, that we are looking at a fraction of all possible observations that are out there in a population, right? So for instance, over here we have this example where we've got restaurants, and restaurants here have information on the annual revenues that they make and the population size in thousands of where these restaurants are located throughout different parts of, say, the city. Okay, and so if we wanted to, say, come up with a linear regression model over here, a simple linear regression model that could relate the annual revenues of a restaurant to the population size where that restaurant is located, well, we would start by taking a sample of size n. In this specific example here, we are looking at 10 restaurants. So 10 randomly selected restaurants out of, a population of size uppercase N. We don't know exactly how many there are. And so here we get information for each restaurant, right? So we get the annual revenue, we get the population size in thousands, of course, and the revenues are also in thousands. And so, well, the first thing to do before we go ahead and create a simple linear regression model for this data over here, the first thing we'd like to do is look at a scatter plot. So we've seen what a scatter plot is about. Here we are looking at uh, in fact, we've got 10 points. So we're looking at the 10 different points of my X and Y values. And so this is basically the red dots here are exactly these coordinates, these XY coordinates over here. So I've got 10 red dots over here. And I'm going to find a line that will best fit across all these 10 points. Okay, so the idea over here is, I'm not going to choose any line. I'm going to choose a specific line that guarantees that the vertical distances of each red dot that I have relative to the line is minimized, right? And hence, I look to use a line of least squares, right? I will use the line of least squares. Yes. Okay. So when I use the line of least squares, I'll be able to find my B naught and my B1, right? As we've seen before. And because now I am using a sample of n observations, in this case, the n observations are 10, then I have to recognize that in my equation, in my straight line equation right here. So I call my y hat. Y hat because this will serve as a point estimate for the true population mean level, for the true population mean level right here, mu of y. This is an unknown. This is only when I have all my population information that I am able to find mu of y. But I don't have all my population information. I only have a sample of size 10. Hence, I use y hat to estimate mu of y. Okay, so with that in mind over here, I now go on to look at, I'm going to review my formulas that were introduced before. Um, So we had seen over here that B1 is determined by this formula right here. B1 here is the covariance of X and Y divided by the sample variance of X, right? So B1 is the ratio of the sample covariance of X and Y to the sample variance of X. And so if we break this down into what the actual forms are right here, this is what it gives me. Okay, so this is what it gives me. So now what I can do over here is cancel out my n minus 1 in the numerator, denominator, and so I'm left with this over here, this form right here. And so this will now be my new B1. Okay, this is B1 right here. And so this can also be called now, it can be called the sum of squares of the x and y's, right? Because I am looking here to multiply the product of the deviations of the x's times the product times the deviations of the y's. So we call the top the sum of squares of the x and y's. In the denominator here, I'm now left with this form right here. So we can call this the sum of squares of the x's. Okay. Now, just one point that I want to bring out before I move ahead is that let's not forget here that because I am dealing with sample data, right? I said here that this y hat serves as a point estimate for mu y, the mean level, which is the population value on, and likewise, the B naught and the B1 are also point estimates. These are point estimates for beta naught and beta 1, respectively. Okay, so B naught serves as a point estimate. It's coming from my sample information, and it's used to estimate the true population value of beta naught. Beta naught, of course, being the y-intercept, right? And the B1 is a point estimate of the true population value beta 1, beta 1 being the population slope. Okay, just a quick little review as well on slope, and that is that you can interpret the slope here as being a measure of the change in the mean value, of y for every unit increase in x. Okay, so if my beta 1 were to be positive, then the the change in the mean value of y, or of the mean level, for every unit increase in x will be positive. On the other hand, if my beta 1, or my slope, is negative, then you can interpret the beta 1 here to be a measure of the change in the mean level of y, or your mean level, um, for every unit increase in x is negative. Okay, so that's just a little note that I want you guys to remember here. Okay, so let's continue on over here. So I said that here we are left now with this form, this equation, which is only, of course, a portion of the simple linear regression model, right? This portion here represents the mean level, or the line of means. The line of means, but of course it's an estimate, right? It's an estimate because we're using sample data right here. And so this y hat will, of course, change for each x value that I put in my equation, right? So each time I put a new x value, I'll get a new y hat. Hence, I have here, this is a more general form. So I have here yi hat is equal to b naught plus b1 times xi for all different possible values of x in my sample over here. So I ranges from 1 to n, and more specifically in this example, it'll range from 1 to 10. Okay, so let's take a look at a little more closely at this sample of 10 restaurants, and let's see what we get over here. So we saw here how we now express B1. B1 now takes on this format. And so this format here, this formula right here is used to estimate a point estimate. It is used to calculate the point estimate for beta 1, right? Once I have my B1, then I can compute my B naught. So B naught here is equal to the y bar. That's the average values of all my y's in my sample. Here I've got 10 values, so I'm going to take an average of these 10 values minus my B1 that I just found right here, times the average value of all my 10 x values, right? Okay, so we implement that. And before we look at the answer here, let's just go to the slides once again and see how these equations can be simplified a little bit more. Okay, so here we have our B1. We recognize this formula right here. And so in the numerator, we've got the sum of squares of the x and y's. The sum of squares of the x and y's can be expressed in this form right here. We point out this form over here because, you know, when you're uh, keeping track of your data, you'd like to have this you'd like to create a row, say, of this information in order to compute sum of squares of x and y more easily, right? If you're going to be doing this manually, that is, right? So in fact, you want to have this added to your column of data, as we see right here. You see here you've got your yi's, your xi's. This is the original data for the 10 restaurants, right? So here we are. And then here I've got this added column of the product of the xi, yi's. So I've got a different product for each row, right? It's always multiplying my xi times my yi. I also want to have another column. I want to create another column, and that is the x of i's squared, where here I'm going to actually square each row of xi and obtain here the products. This will be used um, for my denominator in b of 1. It'll be used for the denominator, which is the sum of squares of the x's. And the sum of squares of the x's can be expressed in this form right here if I wish to calculate my sum of squares of the x's manually. Okay, so here we are. Now let's go back to our example right here. So after having used all these formulas and shortcuts and all that, I now come up with my general formula, y hat. Okay, so this formula right here is following this form right here. It is following this form that I have right here. And so I have over here my B naught is equal to 183.31. Of course, this is rounded to 2 decimal places. And then I've got over here my B1 is equal to 15.596. Okay, so this is the general form. And so what will happen here is that as I plug in different x values, then I will get different yi hats, as we see in this general form right here. Okay. Okay, so here we are. So now I have um, my mean level, or my line of means that is estimated from my sample. It is this black line right here. And these red dots are showing the actual y values that I collected from my sample of 10 observations. So let's not forget, you know, we did have observed y's, right? So here we are. The first one is 527.1. It is this red dot right here. And let's just go take a look over here and see. Uh, so we see not too clearly, but we can see that the red dot here, this 527.1 for the first y value, is just above the mean level line, right? Or the line of means, right? And then the next point here will be just below the line of means, right? So you see how each observation here, each y observation varies about the line of means. Okay. So let's not forget that this line of means is used to explain y, It is also used to predict y, right? You can use it to predict y. So for instance here, I've got, a range of values for x. My range of values in my sample for x are, let me just scroll down, and here we are. My range of values for x ranges from 20.8 thousand to 64.6 thousands, right? That's my range for population size. And so, here, if I were to now test out my line of means, my estimated line of means, okay, this is my estimated line of means, okay. If I were to test it out, then let's see here. If I were to use an actual x value, so in our data, um, let me just go show you right here. In our data, uh, so this data set right here is exactly the same one that I have in my document, okay? If I were to use the point 32.3 for x, I know that uh, my predicted value of y um, I'm, I'm sorry, my observed value of y will be 767.2. That will be the observed or actual value of y when x here is equal to 32.3. But what will the predicted or expected value of y be when x is 32.3? Well, let's just go see over here. At x equals 32.3, my predicted or expected value will be this right here. So 183.31 plus the 15.596 times my x, right? I'm plugging in basically my estimated line of means or my estimated mean level equation right here. And so I get this value of 687.06. This 687.06 is my predicted or my expected value for y. Okay, so if we look here on the graph, this would be in fact the third point here in my x, in my sample of 10 points here. It would be my third point, and so here I've got my actual observed y value. We said here the observed, yeah, okay, the observed value here we said was 767.2, right? So there we are. This is the actual observed 767.2 versus the expected 687.06. So in other words, at this point here, my line of means, my estimated line of means is under predicting or underestimating the y value, the actual y value that it actually is, right? Um, okay, and it is underestimating because my line of means here, the point of 787 is inferior to the observed value. Okay. Uh, now that is when I am using an actual x point that lies in my sample. But in my interval of x values, okay, we said again, let's go look at our interval of x values here. So we said the interval of x values that we have lies between 20.8 and 64.6. Call this, if you want, what generates the experimental region in my graph. So between 20.8 and 64.6, you can call this the experimental region. Okay. And so inside my experimental region, I could I could do some interpolations. Okay, I could ask myself, well, between 20.8 and 64 point, what was it again? 64.6. Yeah. What if I wanted to know what is my predicted y value for an x value that lies in between that range? So here I'm going to take an example of 47.3. 47.3 does lie in my experimental region. And so when I plug in um, my estimated line of means equation, okay, I get this value of 921. Here we are. So this will only provide me, though, with an expected or a predicted value for y. I cannot compare it to an observed y because I do not have an x value corresponding to 47.3, right? Okay, so make note of that. In the experimental region, that is the range that is defined by your sample x values, you can do some interpolations in there. Okay, now what about here? Yes, so here I just want to explain to you how, from this previous graph right here, we see how, each observed y, that's the red dots, we see how they deviate from the estimated line of means, right? We see these deviations right here. And so these deviations are what we call the residuals. They are the vertical distances uh, between each observed y and its corresponding line of mean value for a given x value. Okay, so here we are. Um, I have now here calculated my predicted or expected y's for each x value, for each corresponding x value in my experimental region right here. And as a result, I can compute my residuals for each observation. So um, notice here how some residuals are in blue and some are in red. This is simply to highlight that when I've got a blue residual, okay, this is telling me that my line of means, my estimated line of means, is under estimating what y should really be, right? In other words, my observed y here is greater than um, my estimated y. Okay. Likewise, when I've got a red value for the residual, this is telling me that my estimated line of means is overestimating or over predicting what y should really be. In other words, here, my observed y is falling below the corresponding estimated y. Okay, you can see that right here. The first point here is above the estimated line of means. The second one, the second observation here is falling below the estimated line of means. Okay. Let's carry on over here. So once I have my residuals, well, I'd like to square my residuals here and then add up the squared residuals. So if I add up my squared residuals across all 10 observations in my sample, I get now a new measure, a very important measure, that is the sum of squares of the unexplained variation. Okay, the sum of squares of the unexplained variation, hence SSE. So just to remind you again how we have here our observations that deviate from the estimated line of means. These observations are deviating. This is reflected by the error component of our simple regression model. Let's not forget that our simple linear regression model is made up of two components, right? We've got the observed value is equal to a mean level, and it's also made up of an error term. So the deviations that I'm getting in my graph are in fact accounting for this error term inside my sample, right? It is my residuals. So here I have my SSE, my sum of squares of unexplained variation. Why do we call it unexplained variation? Well, it is for the simple reason that um, there is some variation incurred from one restaurant to another, right? And for reasons that are not explained by the model, right? So the model is able to explain or predict um, annual revenues, Y, to some extent, but then there is that error or random component that also comes into play. So that error or random component that we're getting right here, this is maybe due to, um, say, the management style that in which each restaurant is run, or say, maybe the opening hours are different from one restaurant to another, so revenues are different, and this is not captured in um, my estimated line of means equation, right? It's not captured by this. It is some other external component that is not part of this equation. So hence we call these differences, or actually these differences here when they're squared, we call it the unexplained variation because we cannot explain it by our model, basically, by our straight line equation. Okay? So let's just continue on over here. So I was talking to you before about the experimental region being defined by um, the range of values that X covers, right, in our sample. But what if I wanted to, go beyond my range of values of, what was it again? It was 20.8 to 64.6. Yes. So what if I wanted to go beyond that range? Say I wanted to know what will be the annual revenues of a restaurant that's got a population size of 90,000 right here, right? Could I use my estimated line of means here to extrapolate and determine what my annual revenues will be? Well, that's a tricky question because the moment you leave the experimental region, there is some uncertainty as to whether or not this line of means is extended. Does it continue to go and follow the same direction with the same slope? That's a tricky question, and so there's some uncertainty over here. What happens if my line of means all of a sudden takes a curve, right? Then if I were to estimate my y value using the original estimated line of means equation, then in fact my answer would be off by quite a bit, right? As you can see over here. So to say that at x equals 90, my estimated y will be equal to this much, that's on the assumption here that my line of means continues beyond the experimental region. Well, that is not a certainty, right? So you have to keep that in mind, okay? Okay, that's for extrapolation. Okay. Now, the next point that I want to cover with you is this right here. Okay, now I'd like to talk to you a little bit about simple coefficient of determination and correlation. Okay, so we know what the correlation coefficient is about. We've seen that before, but we're going to talk about it some more now. And now we're introduced to a new measure, and that is the coefficient of determination. So let's say now that I want to see how good is my estimated regression model? How good is it really performing, right? So the idea here is I'm going to compare my regression model to a very basic benchmark model. That very basic benchmark model will be y bar. y bar. Let me just zoom in here, and here we are. Y bar is in fact equal to 860.31. This is in my sample, of course, my sample of 10 observations. So when I take my 10 Y values in my sample, this is the Y bar that I'm getting. And so this is how my data points would vary about a very basic model of Y bar. Imagine if you had Y bar to predict your Y values, your annual revenues, right? What would the variation be here? How far would my observed Ys vary from my Y bar, right? So there is such a measure, um, and that measure is called total variation, or SST, sum of squares of the total variation. Okay, so let's take a look over here. So here we are with our original data right here for our sample of 10 restaurants. We've got our X values and our Y values, the same as before. And so here we see that our Y bar, if I were to use this model here, this very basic model, boring model of 860.31, so each time, I want to predict a Y value for a given X value, what this says is, well, at X equals 20.8 thousands of population, I can expect my Y value to be 860.31. Um, and say at a population size of 45.1 thousand, then again, I can expect a Y value, annual revenue value of 860.31. And of course, this is in thousands of dollars, eh? So this is a very boring model. Okay. Now, it gets a little more interesting when I start to take the deviations. So how far is each observed Y deviating from my uh, average value here of 860.31? It's these vertical bars that you see right here. And so I get these actual values in this column. Then if I were to square these deviations, okay, and sum them up across all 10 observations, I get a new measure here. I get this sum of squares of the total variation. So this is the amount that I'm getting right here. It's a pretty big number, 495,776.51. Okay, that's a pretty big number. Okay, so then let's remember again what the unexplained variation is. We looked at that before, but we'll look at it again. That's the SSE, or the sum of squares of the unexplained variation, or the sum of squares of the errors. Okay, so here we are. So this is what it looks like right here. And so here we get once again our SSE, right? We did that before. We do it again. We get that same value of 30,460.21. Okay, so how do these how are they related, these two values? Okay, well, I'm going to show you something here. Here we are. So how they are related is all the answer lies in this graph right here. Okay, so we've got a lot of information in this graph. Here we recognize our Y bar. That's the average value right here. Okay, the Y bar is in fact the sum of these types of square deviations. Okay, that's the SST. And so this is measuring the distance between an observed point and this benchmark Y bar value. Then I've got in here my sum of squares of the unexplained variation. Well, okay, here's my regression line. This is how it is relative to my Y bar. Okay, this is just a very general example. Okay, so this is a Y bar, this is my regression, my estimated regression line right here. And so the distance that I measure between each observation and the regression line. So when I square these deviations and sum them up across all my n sample points, I get here my SSE. And so somewhere in between these two lines, the regression line and the very basic benchmark y bar line, lies a component here which we call the sum of squares of the explained variation, or SSR, right? So you can also call this the sum of squares of the regression variation, hence the R over here, okay? And so this is, in fact, uh, the sum of the deviations of your fitted y value or your estimated y value for a given x. So for this x value right here, if I had an x value right here, that gives me a corresponding observed y value. Well, I would also get here a corresponding estimated or expected or predicted y value, right? I would get here a corresponding y value. We call this y value, once again, y of I hat, right? So we've seen that notation before, and here it is again. So I'm looking at the deviation here between my expected yi hat for a given x value minus here the benchmark value of y at that same given value of x. Now we know that this y bar value will be the same for all x values, right? That is what this benchmark model is all about, right? And so what we can also say further is the following. We make this conclusion, okay? We say that the total variation in the end, that's my SST, is equal to the unexplained variation, that's my SSE, right? The SSE, plus the explained variation. So that is now my new measure that I'm looking at. That's the sum of squares of the regression variation, okay, or also called the explained variation. Explained because here I know where this variation is coming from. It's coming from my regression line, right? Hence it is explained. Okay, so this is an important formula that you want to note over here. And so with this relationship here in mind, we can now move on to define what SSR is. So SSR in the end is simply the difference between my total variation in the sum of squares minus my unexplained or error variation in the sum of squares. And so it gives me this value right here. Okay. So notice here that in the specific example we're looking at with the 10 restaurants, the sample of 10 restaurants, we get here an SSR value of 465,316.3. Okay, just to compare here with the other values. So I had here my SSE was 30,460.21, and I had my SST was 495,776.51. So you see how when you subtract SST minus SSE, you get your SSR. Okay. And so now comes the interesting part here, and that is, well, if I have all this information available, I can now determine the coefficient of determination. The coefficient of determination is represented by the symbol r square. R square here is the proportion of my total variation in my dependent variable across all n observations in my sample, okay, relative to the total variation in my simple linear regression model. Okay, so here we have basically r squared is a ratio of the explained variation, okay, relative to the total variation. So once again, r square is the proportion of the total variation in y uh, explained across, found across all my n sample points in my sample, okay, that can be explained by the regression model. It is a proportion. So in other words, I am comparing this SSR to the total variation that exists in the simple linear regression model. So let's not forget that SST, once again, SST is made up of SSE, that's the unexplained variation, and SSR, the explained variation. Okay, so here we are. And so here we see, notice here how I I put here in red the yi hat to 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 get your attention on this, because this the yi hats will vary for each x value in my sample, right? So each time I get a new x value, I plug it into my estimated line of means equation, and I get a different yi hat, right? And so I take the deviation of each observed yi minus the estimated yi hats, and I square these deviations, and I sum it across all my n or 10 observations, in this case in my sample. In the denominator here, I'm simply taking deviations of each observed value relative to the benchmark model of y bar, which remains constant for all x values, right? So in this case, we said that it was, let me see, it was 860, I think, 0.31, if I'm not mistaken. Let's just go back quickly. Yes, 860.31 right here. Yeah. Okay. So now let's carry on here. So a little bit more to be said about the coefficient of determination, a very important measure in um, regression analysis. Okay. So this tells you to what extent your model is able to explain the variation in y. That's the bottom line. Okay. So the higher your r square value is, in other words, the closer your r square is to 1, this means that your simple linear regression model is explaining more of the variation in y than, say, the random component, the unexplained variation. Okay? And on the other hand, the closer r square is to 0 means that your simple linear regression model cannot explain a lot of the variation in y, okay? But rather it is the unexplained component that is explaining that the unexplained component that is really driving the variation in y, okay? So just remember this equation right here. R squared equals a ratio of explained variation to total variation. Okay, so R squared, well, that looks a lot like the coefficient, the correlation coefficient that we'd seen before, right? In fact, the two are related. So the correlation coefficient is simply R. And and so here we've got whoops. Here we've got here our R, let's not forget, is defined to be the sample covariance of x and y divided by the sample standard deviation of x times the sample standard deviation of y. Okay, that is R. And so if we elaborate on that, let's go back and review the formulas. So the sample covariance of x and y we had seen before is in fact equal to this formula right here. And in the denominator, if I were to take here the product of the sample standard deviation of x, that's this one right here, times the sample standard deviation of y, that's this one right here, then, this comes out to this. It reduces to this. Once again, the n minus 1 cancel out, and so I am left with this form right here. And so I can generalize now my R correlation coefficient to be equal to sum of squares of the x and y's divided by the square root of the sum of squares of the x times the sum of squares of the y's. Okay, so that is how you define R. Let's not forget that R, of course, varies between -1 and +1. Okay. What's neat also about R is that you can say that, in fact, it is equal to the square root of your coefficient of determination, right? R square here is the sample coefficient of determination. So if I take the square root of that, I can get my correlation coefficient. There's just one little problem here. The correlation coefficient, let's not forget, can be negative or positive, right? So how do we decide? Well, we decide based on our slope, our estimated slope, B1. If my B1 should be positive, then I will put a positive sign in front of my square root of coefficient of determination. Okay, that's the rule of thumb here. If my estimated slope B1 should be negative, then I will put here a negative sign in front of my square root of coefficient of determination. Okay, so that's just something to know. So you can compute R directly with your data if you're able to get that information, or if you're only given the coefficient of determination, R squared, then you can get your correlation coefficient by taking the square root and then adjusting with the proper signs depending on your estimated slope. Okay, and that's it for now. Thank you.